Like ideal gas law is PV equals nRT. So P stands for pressure, V stands for volume, N stands for the volume of moles, T stands for the temperature, and R stands for the gas constant. So so the gas constant, it can take many forms, as you can see here. They're the same thing, but here we see it in different units. So here we see it in joules and kelvins and moles. Over here we see it in liters, torrs, which is another, torrs is another unit for pressure, and kelvins and moles. And over here we see liters, I believe this is atmospheric pressure, and kelvins and moles. So ATM and torrs, they're both the same. They're both units for pressure. All right, so that is the gas constant. So usually when we're plugging the gas constant into an equation, we look at what values we have in the equation as of now. So let's say you know what kind of units you'll be using for the volume and the pressure and the temperature, right? So if you're using liters and atmospheric pressure and kelvins for your current gas problem, then you will want to use this one, all right? This last one, 0.08206 times liters times ATM times kelvins times moles over moles, right? So that's because these have the right units. So you kind of want to match up the units as kind of a case-by-case scenario. So like if you're, so it's kind of for convenience, right? So because you can convert atomic pressure to torrs, but I mean, if you already have atomic pressure, then you want to be using this bottom equation because it's the easiest to use. So basically, you choose which gas constant will give you an easier time for the problem that you're solving right now. All right, so we're going to move on. Right, so these are different pressure units, as I said. So atmospheric pressure equals 1 atmospheric pressure is equal to 760 torrs and 760 millimeters Hg. So these are all pressure units. Right, these are all the different pressure units. And by the way, the gas constant is on the AP chemistry. I believe it's called the equation sheet, the equation and values sheet or something. This is on the equation and values sheet, so you will be able to find the gas constant on there. So you do not need to memorize this. All right, it's a lot of numbers, I know, so you don't need to memorize this. Right, all right, so for temperature, right, so remember how I said that you kind of use whatever units that best suit you, that is available here in the gas constant equations. So however, for temperature, you always want to use kelvins. All right, so you see the K over here? These K stands for kelvins. Do not use Celsius for gas problems because Celsius, it just doesn't convert. It does convert. So here's the conversion table. It's K equals Celsius plus 273, but over here you always want to be using kelvins. If you're not, if the problem gives you a Celsius or it gives you a Fahrenheit, you want to convert that to kelvins before you plug the values into the PV equals nRT equation. So yeah, so definitely, like on the AP exam, they often give you a Celsius unit rather than a Kelvin's unit. So you do want to be sure and double check that you do have a Kelvins instead of a Celsius or Fahrenheit. All right, that's one very common mistake that a lot of students make. Like they forget that they're supposed to be using Kelvins, or they just, they read it wrong. So you do want to double check and make sure that you're using Kelvins. All right, so again, this will all be on the AP chemistry equation sheet, but be very, very, very familiar with PV equals nRT. Because this equation is it's going to pop up everywhere, and it will save you so much time if you know it by heart, and if you know how to use it and when to use it. I know for the multiple choice, the MCQ on the AP exam, you speed is key, and knowing this equation is just absolutely important. I would say this is probably one of the most important equation, if not, I think it is the most important equation for AP chemistry, so that you want to know by heart. All right, so we're going to go over gas stoichiometry at STP. So STP is equal to standard temperature and pressure, and that is equal to 1 atmospheric pressure and 273 kelvins. All right, sorry about this box. I think there's going to be more text that's going to pop up. All right, so when temperature and pressure is at STP, these are some special conditions, all right? So this is something that you want to know. So when a gas is at the standard temperature and pressure, 1 mole of gas takes up 22.4 liters. So so if you ever see like 1 mole of like hydrogen gas, or 1 mole of oxygen gas, or any like 1 mole of gas, they would at standard pressure and temperature, they will all take up 22.4 liters, no matter what gas you're looking at, no matter what element you're looking at. So that's pretty cool, right? So all the different elements, if they are all at the same, or if they're all at the standard temperature and pressure, which is 1 atmospheric temperature and 273 kelvins, they will all take up 22.4 liters of volume in space. All right, and so this is kind of the unit conversion equation that we use. So 22.4 liters over 1 mole. So here, let me show you an example of like how we would use this. So here we have 22.4 liters of oxygen molecules at standard temperature and pressure. And so if we see this, right, 22.4 liters of oxygen gas at standard temperature and pressure, we will know that that equals 1 mole of oxygen gas molecules, or molecule. That equals 1 molecule of oxygen gas. So if you ever see that, if you ever see, oh, this is like, if the AP exam ever gives you this much oxygen gas and they tell you that it is at STP, standard temperature and pressure, then you automatically will know how many moles there is. So here is another example. So hold on. All right, so let's say we have 3 moles of helium gas. All right, and we know that it is at standard temperature and pressure, so it's at 1 atmosphere of pressure and 273 kelvins. Then we know that this equals 67.2 liters of helium. So we know that this much helium takes up this much volume, or this much space. Okay, so later on you'll see in stoichiometry, or in the ideal gas law. Right, let me go back to the ideal gas law slide. So, if we knew, like, oh, we have 3 moles of helium, right, and it is at STP, it is at standard temperature and pressure. So we know that 3 moles of helium, I believe it was like 67.2 liters. I forgot. I have bad memory. Yeah, let's say 67.2 liters. All right. And then so we know how many moles there are. So there's 3 moles. Then we also automatically know that there are that helium takes up 67.2 liters. So we automatically know the volume amount, right? So that's how we would use the STP rule put it into the ideal gas law. So if we ever need to convert things, it's very easy to be able to reference it that way. So even if the AP exam doesn't tell you, oh, this is 67.2 liters of helium, right? You would automatically know that it is 67.2 liters of helium, because it is at STP, standard temperature and pressure, right? So let's do another problem. So let's say the AP exam told you, oh, you have 11.2 liters of nitrogen gas at STP, right? At STP is the key here to using this equation, all right, or this unit conversion thing. So yeah, so we know, so if we know the volume of nitrogen gas, then we automatically will know how many moles of nitrogen gas there is, or there are. And here it's, over here it is 0.5 mole of nitrogen gas. So, so this is a very handy little tool that you want to use whenever you see STP come up, and whenever you're supposed to know the mole of something, and they give you the liters, or they give you the volume, or you want to know the volume and they have given you the moles. All right, so if you guys have any questions, feel free to drop in the chat box. Am I making sense so far? Give me a thumbs up if I am, or just say yes in the chat box if you're following along right now. All right, so I'm going to move on. I'm assuming that you have no questions. If you do have questions, drop it in, as always. All right, so now we're going to be talking about, actually, we're going to be doing another practice problem. This one is a bit longer, all right? So, all right, so we have two, all right, so this is the equation, and the question is how much oxygen, or sorry, excuse me, how much hydrogen gas is needed to react completely with 8.0 liters of nitrogen gas at STP. So you see here at STP, that's the key. So we know that we can use the unit conversion thing of, of moles to liters. So here we are asking for how much hydrogen gas we need, all right? And basically this amount is very dependent on this amount. So this is the limited amount, right? So we know we have 8.0 liters of nitrogen gas. So so we have to come up with how much hydrogen gas we need to make sure that all of the reactants are used up, all right? So all of it is converted to the product side. All right, so first thing first, we want to find out how many, I'm going to go backwards a bit. First things first, we want to find out how many moles of nitrogen gas we have, right? So before, like with any stoichiometry, not just gas, but with any stoichiometry, we need to have we need to have moles as the units, or as the values being evaluated here, right? So the ratio that is presented over here in this gas equation, or in all gas equations, they're all used when you're using the moles, or number of molecules, right? We're not using masses to compare. So we see that we have 8 liters of nitrogen gas. And remember at STP, 1 mole of gas equals 22.4 liters of gas, right? So we're going to convert this into moles. Okay, so that means we're going to be putting 8.0 liters. I'm going to divide it by 22.4. All right, so this is a unit conversion equation, you can see, and it's going to end up with 0.357 moles of nitrogen gas. Okay, let me know if you guys are still following along. So we're just trying to find the amount of nitrogen gas we have. Okay, and the ratio here, you can see, is 2 nitrogen moles to 3 moles of hydrogen gas. So we know that this ratio is necessary for it to fully react, right? Excuse me, this is the ratio for which they react. So this is how they react. So every 2 moles of nitrogen is going to react with 3 moles of hydrogen, right? But if we do not have enough hydrogen, then not all 2 moles are going to be used up, right? So in order for it to fully react, we have to have this ratio perfectly. So now if we were to put this down here, 0.357 moles of nitrogen. If we have the same like ratio going on over here, then 0.5357 moles of nitrogen gas is going to react completely with 0.536 moles of hydrogen gas, right? And so this is our answer. So we need 0.536 moles of hydrogen gas in order for this scenario to fully react, or for all the reactants to be used up. Okay, so for all of the nitrogen gas to be fully used up. All right, and now we're going to move on to the next slide. So now we're going to be talking about the limiting reactant. All right, so we're actually using the same equation as our last slide, but this time we're going to be asking, what is the limiting reactant? So what is the reactant that is keeping us from making more and more and more products, right? So what is the reactant that is keeping us from making an infinite amount of products, right? So if you can see here, like if we had infinite amounts of both nitrogen gas and hydrogen gas, then we will be making infinite amounts of this product here, right? But we do have a limit in this case, because we can see here we only have 8.6 liters or 8.0 liters of nitrogen gas, right? So this is kind of limited. So we only have this much, 8.0 liters of nitrogen gas. For hydrogen, we don't really have a limit. They didn't tell us that we only have like 1 liter or 2 liters. They say they haven't told us like how much hydrogen we have. So we're going to assume that we have a limited amount of hydrogen. However, we have a limited amount of nitrogen gas. So in this case, because we have a limited amount of nitrogen gas, we are not going to have an infinite amount of products being made. All right. So over here, we're going to find. So I believe this is the same. Yeah, this is all the same. So, so you can see. I'm going to go back a little bit. So we only have 0.357 moles of nitrogen gas, right? After converting the 8.0 liters to the moles, because it is at STP. So remember, there's the conversion thing going on. So we only have 0.357 moles. So that is kind of the cap, right, for our equation. So that is, since that is the amount of nitrogen that we have, that is the cap for the entire reaction. Okay, so we know that hydrogen is unlimited. However, nitrogen gas is the limiting reactant. Right, so here's the question. What is the maximum amount of NH3 that can be produced with 8.0 liters of nitrogen gas and unlimited hydrogen gas? So we have the same amount of nitrogen gas over here, and the unlimited amount of hydrogen gas. And this is the same, I'm just basically copying and pasting the same scenario. But now we're asking, like, what is the maximum amount of products that we can make? So what is the number of moles of NH3 that can be made over here? And so the maximum product, so to maximize a product, that is when the limited amount of nitrogen gas is exhausted. Let me know if you're still following me. If you are having any questions or having any problems with certain parts of this this practice problem, then let me know. Feel free to drop a question in the chat box. All right. So we know that we have the maximum amount of product when our limited supply is all exhausted, right? So our limited supplies, our limited value right now, it is, all right, awesome. All right, it is nitrogen gas, right? So we know that the ratio here is 2 moles of nitrogen gas with 2 moles of NH3. So so we know that once this is all used up, right, we're going to produce 2 moles of this. So it's like this is the ratio. So after we use up all this, we get this much of NH3. So that means that 0.357 moles of nitrogen gas, which is right here, is going to, if it were to fully react, it is going to produce 0.357 moles of NH3. All right, so that is the maximum amount of NH3 that can be produced. All right, so now we're going to go over the ideal gas law. So a little bit of PV equals nRT practice. So find the volume of 32.0 grams of oxygen gas at 305 K and 33 atmospheric pressure. So first of all, we're going to list off all of the values that we currently know so that we can keep track of them. This is very useful on the AP exam, by the way, because a lot of times they'll be having maybe like 3 different pressure values in the practice problem, and it may be for different stages of the reaction. So you do want to keep track of all these values and, you know, put a little 1, a little I believe it's called a sub number or something, a little 1 under here, or a little 2 under the P, just to keep track of like which pressure is which. Because you do not want to be messing up your values, because it's so frustrating when you've already figured out this whole equation and you realize, oh wait, I plugged in the values from the wrong step of the equation, right, or the wrong step of the reaction. It's just so frustrating, especially on AP exam. All right, so, and you do not want it to happen on the AP exam. All right, so anyways, we're going to go back to the problem. So we know the temperature here is equal to 305 kelvins, and the gas constant we're going to be using is 0.08206 liters times atmospheric pressure times over kelvins over moles. So this means, oh, and by the way, remember that to use the gas constant, you want to find the most convenient way of using the gas constant, right? So if you're using values of atmospheric pressure and liters for pressure, or for your current equation, for your current scenario, then you want to find the right gas constant for that, for your practice problem, or for your problem. So over here, you can see that 32.0 grams of oxygen gas molecule is equal to 1 mole of oxygen gas. All right. So, so we're first converting it to moles, right? Because for the PV equals nRT, we don't have a mass value here. We have the N, which is the moles. So you always want to convert the masses to the moles. And then we know the N, so now we know that the N value, which is the moles, it is equal to 1 mole, right? And PV equals nRT, if we manipulate the equation, we will come up with V equals nRT over P. So we're bringing everything else to one side, and we're leaving V on one side. So after we plug in all of the different values that we have over here, we'll have volume is equal to 0.758 liters. All right, so if you guys have any questions, feel free to put it in the chat box. I'm happy to answer them as we go. So we want to use PV equals nRT for each component of a chemical equation. All right, so when we're talking about gas law, right, so we want to have, so there's like hold on, let me just show you an example. So this part, right, you'll have to use PV equals nRT for this, and PV equals nRT for this, and PV equals nRT for this, if you want to find out like their specific like moles, right? Unless they're at different, I guess, like if they're all the same, if they're all the same temperature, then it's a bit different. But if you are adding in, let's say you were mixing in nitrogen gas and hydrogen gas, and they both come in different pressures, or they both come in at different temperatures, right? Then you do want to use the equation individually for each to figure out like how many moles or how many like volume, how much volume to take up and all that. So so it's not like you use PV equals nRT for the whole equation. Like they don't necessarily have the same like V values or the N values for the whole equation. All right, so you want to treat them separately. So for example, let's say I need the volume of nitrogen, gas, all right? So I'll use nitrogen gas's data, which is the pressure and the number of moles, to find it, right? So I'll have to use nitrogen's data in order to find its own volume, not hydrogen's data, right? So, I can't use hydrogen's volume or hydrogen's pressure or hydrogen's number of moles in order to find nitrogen's volume. So normally the temperatures for one side of the equation are the same. So usually, like, let's say we're reacting a gas that, like, after it reacts, it produces a product that is at a higher temperature, right? This is the case of a lot of different reactions. So, like, let's say that it changes temperature, right? So after the reactants react, the product is at a higher temperature. Then usually that means that this side of the equation is one temperature and this side of the equation is another temperature. So this is usually the case. So you do want to be aware of that, because sometimes the AP exam does give you equations where the temperatures change. All right, so yeah, so these two are going to be the same, and these two are this one is going to be basically on the product side, which means they are basically not on the same side of the table. All right, so now we're going to go over this gas stoichiometry rule for all gases. So this is a very cool thing, all right? So you can treat volumes and pressures like moles in gas stoichiometry. There's something that kind of blew my mind. I was like, wait, what? Hold on. Wait, I have a table right here. So you can treat, oops, okay, my size is kind of functioning weird. So you cannot treat masses this way, by the way. So if you have like 6.0 grams of oxygen, you cannot treat it like moles. All right, this is always a rule. So do not treat masses like moles, because the same mass will mean different number of moles for different molecules. And so like, let's say we have 0.6 oxygen, or 0.6 grams of oxygen, and that does not equal 0.6 grams of hydrogen, right? Because there are different sizes, they have different weights, they have different masses. It's all like the number is all different, or the mass is all different. So over here we can see this is kind of like a really handy table to relate all the information up here. So so usually when we read this, we would say 2 moles of CO, right, plus 1 mole of oxygen gas equals 2 moles of CO2, right, carbon dioxide. However, in gas stoichiometry, we can also read it as 2 atomic pressures of this, and 1 atomic pressure of this equals 2 atomic pressures of this, right? And 2 liters of this plus 1 liter of this equals 2 liters of this. So I think that's pretty cool that you can kind of use volumes and pressures interchangeably in gas stoichiometry. But you do want to be aware that, like, if the temperature changes, right? So if the temperature changes over here, then that will affect the volume, right? So it may not, so this may not work, right? If the temperature is changing, or if the pressure is changing, right? And it may not work over here either if the volume is changing, because remember, if the volume is decreasing, if the container is like constricting, right, then you're going to have a much higher pressure value. So if you were to manually constrict the volume, then this would not be that, like, 2 and 1 equals 2, right? It would not equal that. However, for moles, for number of gas molecules, it will be always the same. So I would say, like, the more reliable unit to use will always be moles, right? Because moles, like, you can't, like, unless they tell you, oh, I'm adding in more moles, where I'm adding in extra this or extra that, then we always know that the moles, they're always going to be the same, because there's no outside, like, additives, right? All right, so we're gonna be going over the gas stoichiometry when we are collecting gases over water. So, alright, so the pressure of gas A, I'm going to call it gas A, alright, that we're collecting over water. So the pressure of gas A is equal to the pressure of the total, like the total container, multiplied by the I believe it's called the molar the molar fraction, I believe. Molar fraction, correct me if I'm wrong, by the way. The molar fraction. So yeah, so the XA, it is equal to the moles of gas A over the total moles that we have in this container. All right. So the pressure of gas A is equal to the total pressure times the mole fraction of gas A. All right. And that is because, like, how much, so basically, let's say we have 10 moles of 10 moles of gases in this container, right? Let's pretend there, I'm going to take my water bottle, actually. So let's pretend there's 10 moles of gases in my water bottle. Then let's say there are two different gases. There is hydrogen gas and there is oxygen gas in my water bottle. All right, so let's say the oxygen gas takes up 20%, or its mass, its total moles. It takes up 20% of the moles of the whole container, or the total amount of total moles of gas. Then we know that the oxygen, or the oxygen gas, its pressure is made up of 20% of the total pressure. So basically, how much, like, of a fraction of the moles that you share determines how much of a fraction of the pressure that you share. So I hope that makes sense. If that doesn't make sense, let me know in the chat box and I can clarify things. All right, so that means that the gas A's mole fraction shows its contributions to the entire gas, right? So gas A's partial pressure contributes to overall pressure in the same ratio as its mole makeup. All right, so P total. All right, so this is called Dalton's law of partial gas. It is P total equals PA plus PB plus PC. So like A, B, and C, they all represent 3 different types of gases. So it could go on. So let's say we had like 100 different gases in this one container, right? So then we would have like 100 different P's over here on this side. However, every single P has its own different pressure. It has its own partial pressure, right? So, but if we were to add up all of these different partial pressures, then that would be equal to the overall, or the total pressure of the container. So all the small individual pressures, they add up to the total pressure. However, you do want to be aware that water-soluble gases like ammonia, hydrogen chloride, and carbon dioxide cannot be collected this way because they dissolve in water. So when we're talking about collecting gas over water, hold on, I'm gonna give you guys a picture actually. So over here, this is when we're collecting gas over water. All right, so we have a gas that is basically boiling, or let's say this is the liquid version of the gas. All right, so we're heating it up, and it is evaporating. So it's going through the tube. The gas is going through the tube, and then it's going through the water and it's bubbling up. All right, so it's going to be bubbling up. So this is how we're going to collect it. So this little end over here, that is the gas that we're collecting. However, when we are collecting the gas, we also have to be aware that when it's bubbling through the water, it also carries with it water vapor. So that's kind of a problem, right? So when we collect the gas, we don't have pure gas anymore. We have gas and a bit of water vapor. They haven't chemically reacted, but it's not. So let's say we have like three atmospheric pressure of gas 1, or of this little amount of gases that we have collected. We will know that this 3 atmospheric pressure of gases that we've collected, it is not equal to 3 atmospheric pressures of gas 1 because it is not pure, right? There is a bit of water vapor that is inside of that sample that we have. So we have to also put into account the pressure of the water vapor. So in this case, I'm going to go back to previous slide. So in this case, that will be gas 1, the pressure of gas 1 plus the pressure of the water vapor. That would equal to what we have in the sample, the total pressure in what we have in the sample. So, so when we're collecting gases that way, we also have to be aware that there are certain gases that are water soluble, which means when they go through water, they basically dissolve in water. So they don't bubble up out of the water anymore. They just basically stay inside the water. They kind of react with the water, right? So water-soluble gases like ammonia, hydrogen chloride, and carbon dioxide cannot be collected in this way because they dissolve in water. So as they're bubbling up through the tube, here, let me show you the picture. As they're bubbling through, they don't reach this upper level, right? They kind of stay in the water. So then you'll probably be only collecting gas vapor. So, or sorry, water vapor, because they dissolve in the water. All right, so this is the partial pressure equation, and it basically means this. It means that, like, for every single pressure over here, right, these are all in respect of each individual gas that we have in a chemical equation or chemical reaction, right? So, so that means that each gas has its own number of moles, and they all have their own little number of moles in here. And if they were sharing the same volume, then they will all have the same volume. If they're on the same container, which in this case it is, so they will be all sharing the same volume and the same temperatures, right? Because, if we're having one container, we won't have like 3 different temperatures in the same container. We will have the same temperature in one single container. All right. So in this case, the only way we can use this is when we're collecting insoluble gases because we're letting the gas bubble through the water. Right, so yeah, the gas bubbles through, but there's also water vapor. And so the water vapor and gas and the pressure of gas 1, it makes up the total gas pressure. All right, so the total gas pressure that we have in the sample right up here, it is equal to the pressure of the water vapor and also the pressure of gas 1. So if we wanted to find the pressure of gas 1, right, we will have to put it into this equation. So the pressure of gas 1 will be equal to the total pressure of the sample that we have minus the pressure of the water vapor, because there's water vapor in our sample. All right, so now we're going to go over a practice problem. So excuse this going on. I don't know why it's here. I think it's a glitch with Google Slides. I'm pretty sure it's a glitch. But anyways, we're going to go on. So hydrogen gas is collected over water at 296 kelvins. All right, so the water's vapor pressure is 21.1 torrs, which is, by the way, torrs is another unit for pressure. And the overall pressure is 30.1 torrs. If hydrogen gas has a volume of 0.5 liters, how much hydrogen is collected? So we're asking for how many moles of hydrogen do we get from the sample that we have. So remember, this is our equation. So the total pressure, the overall pressure, is equal to the overall pressure of the water vapor plus the overall pressure of the hydrogen gas. Or sorry, not the overall. I'm saying overall too many times. The partial pressure of these two. So we know that the overall pressure over here, it is 30.2 torrs, 30.1 torrs. 30.1 torrs, and is equal to the water vapor pressure, which is 21.1 torrs, and plus the partial pressure of the hydrogen gas. So if we were to put the pressure of the hydrogen gas on one side, then it would be equal to 9.0 torrs. So let me know if you're still following along. If you ever need me to clarify any part of the material that I'm going over, feel free to just like let me know and just say like, oh, I have a question about this, or something you want me to repeat. All right. So if you're still following along, can you just say like good, like, or yes, I'm still following along, so that I know. Okay, so I'm gonna move on. If you have any questions, feel free to just pop in a question, and don't be afraid of stopping me. All right. So the equation that we're going to be using is PV equals nRT. Again, this is the king equation, right? This is the equation that you will be using, you are guaranteed to be using on the AP exam. And this is the equation that is so handy. Like you can use it, you can plug it into basically any gas equation, and it will give you some very valuable information on like some other things. So, you know, if you have, if you have like if you have 3 of these units down, so if you know the pressure, you know the volume, you know the number of moles, then you will automatically be able to find out the temperature of this gas. So it's very easy to use. All right, so P, we know for hydrogen gas, since by the way, we're trying to find out the N of hydrogen gas. So we're trying to find out the number of moles that hydrogen gas is taking up, or how much. We're trying to find out how many moles of hydrogen gas that we have. So so we know that P is equals 9.0 torrs because we're talking about hydrogen, and we know the volume is 0.5 liters, right? And we also know that the temperature is 296 kelvins. So again, if we have the sample, right, if the whole sample is 296 kelvins, then you know that the hydrogen sample, or the hydrogen part, is also 296 kelvins. Because like one sample is all the same temperature. They're not going to be like different temperatures unless they're reacting and making up and reacting to make a product that has a different temperature. Then that will change the overall temperature of the sample. All right, so the gas constant we're going to be using is R equals 6.36 liters torrs divided by kelvins divided by moles. All right, so this is the R constant that we're going to be using. So I kind of wrote it out on a piece of paper. So PV equals nRT. So, oh, by the way, so on the AP exam, anyways, I'm gonna first ask you guys a question. So when you're doing these practice exams, are you putting it on paper? Like, are you writing it all on paper and like keeping track of the units and all that? I know it's like a lot of units to keep track of, right? So like a lot of times you just try to like cross it out or try to simplify things before we put it on paper, maybe in our own heads. But I do want to encourage you to like write it down, because when you're taking an AP exam, the graders, if you did it all in your own head and you just wrote down the final answer, the graders are going to give you a 0 for that answer, even if you got it right? Because they want to see you write down every single step. Or not like every single like baby step, but like every single major step that you're taking. That is reasonable, right? So yeah, so let's say if you wanted to put like if you wanted to isolate N, right, then you have to write that down as as part of your solution. So I'm going to show you like how I did it, how I wrote down every single step that I took within reason. So yeah, so first of all, I wrote down PV equals nRT. Always write down the equation that you're using, all right? Don't just like randomly put in this whole set of equation, this whole equation with the units plugged in, because you want to show them that you're using the right equation, or you want to show them what equation you're using. That way, like it makes sense, like as to why you're using it. And then, yeah, so basically I plug it all in. Hold on. I plug it all in. I put in the P, the pressure, the volume, the N, the R constant, and the temperature, right? So we don't know the N, and we're trying to find out the N. We're trying to find out how much hydrogen gas we have. So I basically put it into a fraction format. So I isolated N, so N equals, I'm not going to read it all out, as you can see, but you can see here that I divided both sides by 6.36 liters of torrs and blah, blah, and the temperature I moved it on to the other side in that way. So basically I have it. So you want to remember to keep track of the units, right? So I have the units all written out over here so that I can show them that when I cross it out, it makes sense. So I'm crossing out the torrs and the torrs, kelvins with the kelvins, because one is on the numerator and the other one is on the denominator. And we're left, and see, like after we cross out all the values, we're left with the moles on the numerator side, right? So a lot of times people ask me, or a lot of times, like I remember when I was an AP chemistry student, I asked my teacher, like, why do I have to show them I'm crossing out all the units? Like this is like so tedious, right? Like we can just do it in our head, or we already know that the number of moles is going to be a mole. It's going to be a mole value, right? It's not going to be a liter's value, right? Because this is N equals the number of moles. Well, my teacher said that, well, and I agree with this too, but if you write out everything and you cross it out, and if you're, let's say that if you're left with a moles and a liters on top, then you know that you did something wrong, right? You know that you probably made a miscalculation because you're not supposed to have the liters next to the moles, right? So having these units out and crossing them out, it gives you like an extra validation that like your value is the right value, right? You didn't make a miscalculation somewhere along the way. So this is very easy to get messed up on, especially if there are lots of steps to an equation. And I know that when I was taking the AP Chemistry exam, there were certain problems that had lots of different steps. And because I was able to keep track of the different moles and keep track of the different units and make sure that I have the right unit for each step of the equation, then I'm more confident like moving on, right? I know that, oh, I have the right value. It's not like, oh, maybe I have the right value, maybe I didn't, maybe I miscalculated. So basically using this method is foolproof, right? It just guarantees you that you're using the right value, and it basically is an extra barrier, an extra thing that validates that you didn't miscalculate. So after I divide 9 by 296 and 6.36, then I am left with N equals 0.0024 moles, and that is our amount of hydrogen gases that we have collected.